Mrs. Fitch here. Today we're going to talk about how high will it bounce. So we're going to look at rebound ratios of when it comes to sports balls. We know that many games depend on how a ball bounces. For example, if basketball rebounded differently, one basketball would bounce differently off of a backboard than another would, and of course this could cause our basketball players to miss their shots pretty regularly. So for this reason, manufacturers have made ball bounciness conform to a very specific standard. So today we're going to investigate that relationship between the height in which you can drop a ball and the height to which it rebounds. Our learning target for today is we're going to talk about how high will it bounce. And to be successful about talking about that question, we're going to be able to take some data, generate that data through a model, and show that model through a table, a graph, and then ultimately coming up with an equation for the data that we come up with. And we also want to be able to calculate the ratio of rebound height to drop height. So here's a list of the bounciness standards for different kinds of sports balls. So we have tennis, soccer, basketball, and squash ball. So we need to start by finding which ball is the bounciest. So which ball is the bounciest? So if we look at the data that they give us, for example, on the tennis ball, the standard is it must rebound approximately 111 centimeters if it's dropped from a height of 200 centimeters. And this goes through on all of them. A soccer ball must rebound 120 centimeters if it's dropped from 200 centimeters. Basketball rebound approximately 53 and a half inches if it's dropped from 72 inches onto a wooden floor, right? And squash ball must rebound approximately 29 and a half inches if it's dropped from 100 inches onto a steel plate at 70 degrees. So ultimately, when we look at the information that they're giving us, we are looking at the bounce and the drop height. So what do we want to do? So we want to make a comparison. We want to compare the bounce to the drop height. So there's a lot of ways in which we can compare things in mathematics. And one way we can do that is we can create a ratio. So a ratio is one number over another number, a real number over a real number, for example. So we can say A over B. So a lot of times we can refer to ratios as fractions. A fraction is a ratio. We're comparing two things. We're comparing A to B. And for our example, we want to, we're looking for how much it's bouncy, how bouncy the ball is. So we're looking for that rebound height over, well, let's call it the start height, or the drop height from where we're dropping it from. So we'll just call it the start height. So in other words, you got somebody holding a ball. My beautiful, I gotta put a smiley face on him, give him some hair too, right? Gotta make this a little realistic. And we're on a floor. So this would be our start height where we're holding the ball up to, and then we're gonna let go of the ball, and the ball is going to do what? It's going to drop. When it hits the ground, what's it going to do? It's going to bounce back up. And it's going to bounce back up to this height, and then it's going to do what? Yep, it's going to start going back down. And then this is going to continue on. So those are, my artistic ability, we're going to make that a little bit more dramatic. We're only going to say it bounces this high, so it doesn't look like it bounced back up to the exact same height. There we go. And then it's going to keep going, right? So this would be our original height, or our start height, and this is our rebound height. So we want to know how high or how far from that original, when it comes to our rebound, how much of it did it rebound? And that's how we're getting our ratio. So if we go back up to, I'm just going to write it right up above on all of the little examples. So a tennis ball has a rebound of approximately 111 centimeters when dropped from 200 centimeters. So when it's dropped a total of 200 centimeters, how far does it come back up? It covers 111 centimeters of that 200 centimeters. Soccer ball rebounds approximately 120. Oops, I'm sorry. There we go. Soccer ball rebounds approximately 120 out of 200. The basketball. So our biggest thing is when we're coming up with these rebounds, it doesn't matter that, for example, our soccer ball is in centimeters and our basketball is in inches, because we're coming up with that ratio, or how much, or it's really like a percentage of how much it rebounds. So what part of the whole distance does it come back up? So as long as our rebound height and our drop heights are in the same measurement, it doesn't matter that the different balls are being measured in different standards or increments. So basketball, it rebounded 53.5 out of 72, and the squash ball rebounded 29.5 out of 100 centimeters. So my goal for you is we're going to pause the video for 2 minutes. I don't even think you need 2 minutes. How about 45 seconds? 45 seconds, I want you to come up with which ball you believe is the bounciest off of these fractions. So push pause. Give it a little bit, and I'll be right back. Alright, I know you guys figured it all out. You paused it, and when we went through, so ultimately what I would have done on all of these is, if anything, I had to put each one of these into the calculator. Well, I guess if I look at these two, if I'm looking at 111 over 200 versus 120 over 200, I already know I can cross this guy off, right? Because that soccer ball is going to be more bouncy than the basketball. I can either do a couple different ways. If I look at the squash ball, I have 29.5 out of 100. If I doubled that up to 200, I wouldn't even be at 60 out of 200. So I know that my 120 over 200 is going to be more bouncy. Now, between the soccer ball and the basketball, I got two options. I can try and get like that 72 up to 200, right? If I multiplied it by 3-ish, right, that 3 would get me to just over 120-ish, which is pretty close to 210-ish, which is pretty close to 200. And if I multiply the top by 3, I'm going to be over 150. So that's one way, or the other way is you can plug it into the calculator to actually turn these into decimals. And when I turn them into decimals, or by making that estimation, I can see that my basketball is going to be the bounciest. So I decided to do a little experiment for you guys. I actually took this little bouncy ball and I dropped it from different heights, and I recorded the rebound height of all of these in my little demonstration that I did. And so now I have all this information and I have it in a table. I can then now take my table information and I can turn it into a graph. So I'm going to do a nice little graph. But before I figure out how to label my axes, I need to figure out which one of the heights, the starting height or the rebound height, which one is going to be my independent variable? And which one is going to be my dependent variable? So I need to figure out if my starting height depends on how high the ball bounces, or does how high the ball bounce or how high the rebound is depend upon my start height. And I am going to go with that my rebound, ran out a little bit of room there. My rebound depends on my starting height. So earlier in the year, we talked about independent and dependent and inputs and outputs and X and Y values. So we know that our independent, if we recall, is going to be our X variable. And so on our little graph here, our X's are the horizontal axes, and our dependent, which is our Y, is our vertical. And so this one is my rebound. When I go to make my graph for my starts, I'm going to look here, and I go from 40 to 120. So I think I could count by 20s. And I'm going to start at 0. So 0, 20, 40, 60, 80, 100, and 120. And I don't know, let's say these are in, what, centimeters? We'll go centimeters. I'm going to put our little measurement on there. And then when I talk about my rebound, if I look at my rebound, I'm going from like 30 to 90. So I'm just going to count by tens. Oops. Don't want to erase everything yet. So 10, 20, 30, 40, 50, 60, 70, running out of room, 80. We're just going to throw 90 up there. I'll just change the color and maybe we can find it. So let's go through and plot these points real quick. And then finishing up 40, 30 would be right about here. So if I just leave my dots the way that they are, this is what we refer to as a discrete graph. So a discrete is just separate points that are on the graph. We want to make this continuous. The difference between like discrete and continuous, like if I was talking about number of shirts and the cost of those shirts are, you're never going to buy a half a shirt. You're going to buy 1 shirt, 2 shirt, 3 shirt. So when you graphed them, that would be discrete because you can't have 2.5 shirts. For us on this graph, now that we have these plots, we can make a line of best fit because with our start heights, we can drop that at any height. We can have any measurement. We can have half inches, we could have quarter inches or centimeters. We could have anything on there. So the difference between discrete and continuous. Discrete are where you can only have, say, whole number items, right? So when I go to draw this line of best fit, I want to try and get this as close as possible to all of these points, but it's going to be a straight line that I'm ultimately going to graph. The one other point I can graph is I know where I'm going to cross the y-axis. And I know that I'm going to cross the y-axis at 0. And I know that because if I put the ball on the ground, so it has a starting height of 0, when it comes to the rebound, I know the rebound's going to be 0. I know it's not gonna come up. It's not. Wasn't that Flubber was the movie, that bouncy stuff? Yeah. So then now I'm just going to try and draw this best fit line. So I'm going to try and get as close and as many. Whoops. And of course this is perfectly straight. And I never can draw straight lines. But we're going to use our imagination. It's getting worse. We're going to use our imagination. I apologize. One more try and I'm done. That's better. A little better, right? That line of best fit that goes through there. All right. So when it comes to my representations, I wanted to be able to do a table. And I did that table because I had a partner assistant with me when I bounced the ball. They helped me measure the rebound height. I was able to put it in a table with my independent variable. So the third thing is I need to come up with an equation. So if I want my equation, I'm just going to go with, let's say, y equals mx plus b. Right? Because I know I have a line, and so I'm going to see if I can do it under slope-intercept form. And when I look at my problem, y equals mx plus b, x and y, those are all of the points that are on the graph. M is my slope, and currently I don't know my slope, but I know I can find my slope. And b is my y-intercept, where I cross the y-axis, and I know that value. So the only value that I need to work on finding is m, which is the slope. So m, is the slope. And to find my slope, I'm looking for the change in y over the change in x. Right? In math, instead of always writing the word change in y and change in x, we can use this little symbol called delta. So delta y over delta x is slope. And I know that you guys have talked about delta y over delta x in your science classes. So ultimately I need to find my change in y over my change in x. So I know these values are my y's because they are my dependent variable, and these are my x's. So I just need to pick 2 points so that way I can find my slope, because my slope would be constant in a line. So let's say I picked, let's go with the first point, and they can be any point. You're just picking arbitrarily whichever ones you want. I'm going to go with the first and the last just for the fun of it, right? So to find change in y over change in x, so change in y would, if you're finding change, you're subtracting. So I'm just going to go for 90 minus 30. My change in x, going in that same order, I'm going to go 120 minus 40. So I am going to come up with a slope that equals 60 over 80. And that's going to reduce down to 3/4. So now when I go back to my equation of the line, I know I have y equals my slope, and we discovered that the slope was 3/4 x for all the x coordinates of the points, plus b. B is my y-intercept, so where I cross the y-axis, and I crossed it right there at 0, so plus 0. So we can just simplify that down to y equals 3/4 x. So one of our ultimate goals on this, we had 3 things when it came to our success criteria. We wanted to be able to represent our data in the form of a table. We wanted to be able to represent it in a graph, and we wanted to be able to represent it as an equation. So we are successful at those 3 criteria. And then the last one was to figure out the rebound ratio, and we were able to find our rebound ratio. We have a rebound ratio of 3/4 for our products, and we found that out even up here when it came to all of ours. All of these were our rebound ratios. If you head on over to our website, our class website at bit.ly/FitchMath, and under today, there will be a short assignment that goes along with this information. I hope you guys have a wonderful day. I'll talk to you later. Bye.